S3. Okay, DynamoDB is Amazon's flagship NoSQL system. This is actually based on a white paper that was written in like 2001 about Dynamo, like the data concept, right? Distributed data consensus data store. Not really sure exactly how to say that, so just roll with me for a second. So this is about basically their completely serverless data store system. Now, there are a number of database options, which you may have heard me refer to before. Amazon loves taking open source databases and making them easy to install. Now, I know you might be like, well, how does that help the open source community? Adoption? Anyway, and by the way, Amazon does contribute a lot of code to these open source communities. So I'm not saying they're saints by any means, because they are a business, but just to say this is that they do try to give back to the community. So we're gonna talk about DynamoDB, developing best practices, troubleshooting, which is pretty much the standard scenario we're gonna be following for the remainder of all the services, right? You're gonna get introduced to it. We'll talk about some best practices, do some troubleshooting. There's the scenario, the lab, for example, and then we're gonna do that, okay? Now, first of all, just know that if you need MongoDB compatibility, they have it. You need Cassandra compatibility, they have it. Elasticsearch, they have it. Like they've got, like I said, a bunch of the open source ones. So, you know, one of the things they kind of key in on a lot is that what kind of data store do you need? Do you need something that's highly acidic and highly transactional, like something that does OLTP? Do you need something that does OLAP? Do you need something that does not only SQL, but maybe does something a little bit more blobby, a little bit more document based, a little more key value based? You know, this is where non-relational databases have exploded in the last 15 years, whereas relational databases have been around since like the 70s. And NoSQL databases tend to have a more flexible schema, but they're also a lot less like consistent when it comes to contention and like being a single source of truth and all that, but they scale better. For the dollar, NoSQL databases will scale way better at the same like hardware than a relational database with, but the cost can sometimes be a level of consistency and relationship. So, you know, typically also, at least from a write perspective, you can only really scale relational databases vertically, meaning you actually make the box bigger. Whereas non-relational databases like Elasticsearch, for example, if you just want more write capacity or read capacity, you just add more nodes to the cluster. That's all. So they mainly support eventual and strong consistency. But just to say this, relational databases support strong consistency. They are not eventually consistency driven, unless you're using something like RAC and you've got something funky set up, right? Oracle RAC. Now, with a relational database, obviously everything is in a row and a column. It has a very strong relationship. In other words, we know how this one table relates to another table, which relates to another table, because there's primary and foreign keys all over the place that kind of like create those linkages. With NoSQL, it's just a blob of data. Everything we know about, you know, whatever, Pink Floyd's Time or whatever song we want to pick, right? The Weeknd's Crying for You, right? So my point being is that NoSQL databases don't tend to follow a strict data structure per se. There is structure, but it's a lot more flexible. Now, if you're looking for a transactional database, your option is mainly either the relational database service, which is highly transactional. You can also get DynamoDB to be transactional as well, both in how you use it. You can also enforce strong consistency. So you can not only do it programmatically, you can actually get the service to enforce it as well. If you need analytics, you want Redshift. Neptune is a graph database. So for those of you familiar with Neo4j, that's what Neptune is really based off of. And then in-memory data store and cache. Well, they're listing Elasticache there. They also have, by the way, managed Redis. So they have Elasticache for Redis if you just want to use the Redis database, which is an in-memory data store. They also have Elasticsearch for search. They have Cloud Search for search. They have a ledger database. There's others out there. They have DocumentDB, which is Mongo compatibility. They have KeyStore, which is Cassandra compatibility. They've got a bunch of other services here, right? So just be aware that there's pretty much a data service for every major popular open source database out there. Now, the relational database service, which is pretty much reserved just for OLTP, for high transactional systems, basically is very familiar because you've got SQL Server, MariaDB, Oracle, Postgres, and MySQL. And Aurora is just Amazon's flavor of Postgres and MySQL. That's it. In other words, they took Postgres and MySQL and put it on a special storage engine. And now Aurora is an option where it actually is 3 to 5 times more performant with the exact same hardware, exact same data set compared to standard RDS, Postgres, and MySQL. Aurora's been around for a number of years, like 4 or 5 years, I want to say now. And they also have a serverless version of Aurora, which is spectacular because now you only pay for the data you're storing. You don't pay for a running compute system. What do I mean by that? Well, if we go back to our EC2 instances.info, which is also known as instances advantage, where we went yesterday to look at EC2 instances, just so you know, there's an RDS tab here, and RDS, the RDS system, the same system we're just looking at here, this system uses EC2 instances, has its ASK unit of capacity. In other words, when you deploy a database, you have to pick a size of EC2 system. You're not going to log into that EC2 box. You can't even see it once you launch it, but it's there underneath the covers and it's running your database, and that's the limit of your performance capacity. In other words, let's say I want to run a test database and I was going to do a T3. It's a DB-T3 micro, et cetera. If I do a 2x large, then that means I have 8 CPUs and 32 gigs of RAM. That's the limit of size of my database. If I want to upsize it, I'm gonna have to switch to a different family type for that database in order to get it to be larger. So just know that you ask for a t-shirt sized EC2 instance that you cannot log into and can't manage right underneath the covers here. That's if you're doing just traditional RDS. Traditional Aurora works the exact same way, except you can have multiple read replicas and multiple kind of masters, if you will, inside of Aurora. There's also serverless version 2 of Aurora, which, sometimes you can run into a cold start issue where it takes a couple milliseconds or so for it to fully warm up, but you can get around that by asking it to be, warmed up at certain times or whatever, right? The version 1 of Aurora serverless, by the way, was absolutely garbage, and version 2, which came out like 6 months ago, spectacular. You do have the same caveat again, like a cold start problem, but again, you can get around that just by pre-warming it or just trickling it. They don't charge you, by the way, for that. They just charge you for the queries that you run, and they charge you for the data that you store. Unlike RDS, which charges you 24/7 for a running EC2 instance under the covers. So serverless is a really appealing option in this space. So Adam, I just realized I saw your questions. I hope that answers your questions about the performance trade-off. In any serverless system, cold starting can be a problem, right? So unless it's been accessed recently, like if it's been hours since it's been accessed, it won't be maintaining a running, like warm system. It'll take a few milliseconds, sometimes up to a second to get started, but you can easily get around that. So still cheaper. So Aurora, by the way, will do multi-region copies. I mentioned this before. It's high performance, 3 to 5 times faster than the standard MySQL Postgres databases. You can create multiple read copies. Your data, by the way, is copied anywhere from 3 to 6 times over. So it's like way faster. You can basically set an on-demand auto-scaling configuration for Aurora, which the database will automatically start up and expand based on your needs. There's a global database option. That's the one that does the multi-region copies. It allows basically a single Aurora database to span multiple regions. You get faster reads locally, And then what it will do is it will converge your data globally. I believe that is eventual consistency. It's not to phase commit like traditional RDS. Redshift, so we're now switching out of RDS, because just remember, Aurora is a subset of RDS. We're moving away from RDS. We're moving away from transactional processing, and we're just giving a single slide to mention Redshift. So if RDS is OLTP, transactional processing, this is OLAP, this is analytics, this is reporting. So Redshift is, I think it can go up to like 3.2 petabytes of in-memory. Could be wrong about that. But basically allows you to run large like data, like concurrency reports, parallelization. It has like an MPP, like a massively like parallel processing infrastructure. You can do locally attached storage. There's like 10 gigabit connections between nodes. It's like ridiculous. Redshift also has what's called a Redshift Spectrum add-on that allows you to read data out of S3. So you can actually run queries against data in S3, and it'll actually pull that data in for its reporting purposes. Now, let me be clear about this. The data that you're going to read out of S3, out of the storage system, has to be in like Parquet, Avro, Orc, Ion, JSON. It can't just be like log data. It actually needs to be, structured and semi-structured in some way. Tab separated, comma separated, it doesn't really matter to me, but it's got to be in some kind of structure. So it will integrate, by the way, with QuickSight and other BI tools. But Redshift is the online like analytics processing engine. Now we're switching gears because we were talking about RDS. We talked about Redshift, and now we're talking about Elasticache. Now Elasticache is a little weird because Elasticache actually has 2 flavors. So RDS has like 5 flavors plus Aurora. Redshift only has Redshift. There's one. Elasticache has 2 flavors. It either runs in the open source database Redis, REDIS, or Memcached, MEMCACHED, Memcached. So Elasticache for Redis and Elasticache for Memcached are just 2 like open source in-memory databases that are mainly used for caching. Now there's also Elasticache for Redis, for managed Redis. So you can actually just run it not as in a cache, but just like as a straight up open source database. You can set up high availability and redundancy. In general, Memcache will like multi-thread really well, but Redis does like pub sub and sorting and ranking. So most people stick with Redis from what I've experienced. If you want a simple cache, people just stick with Memcache. But if you need something that does like advanced data capabilities and data types and whatnot, then you're going to use Redis, REDIS. Okay. They are going to ask you questions. They're going to say things like, hey, I need a multi-threaded in-memory data cache. And it's like, do you choose Redis or Memcache? It's going to be Redis. I'm sorry, it's going to be Memcached. Memcached multi-threads, but Redis will scale from a node perspective. So it scales horizontally better. So Redis tends to be kind of like the popular choice for caching and session management. So fully managed, same thing in that you choose like sizes of systems, nodes. But again, you don't manage the nodes. This is fully managed system. So that all gets handled for you. So Elasticache is basically an in-memory caching system mainly used for database caching. So then we'll talk about Neptune. Neptune is basically, it supports Open Graph API. So this is the Neo4j compatible system. If you're familiar with SparkQL or Tinker or what's the other one? Gremlin, I think it is. Neptune basically powers fully managed graph databases, right? So this is like graph databases are optimized for storing billions of relationships and being able to query the nature of those relationships within milliseconds of latency. So it's ideal when you need to create relationships between data like quickly, like people or content, and you want to query these relationships. So, if you needed to do this, by the way, inside of an RDS database, you'd have to need multiple tables with multiple foreign keys, and you'd be executing queries, multiple joins to bring all this data together. It's a lot more complex and harder to do that kind of thing inside of a traditional database. With a graph database like this, graph databases are not so concerned about the data, they're concerned about the relationships between the data. So nested queries and complex joins aren't necessary when you use a graph database. So consider a graph database to be an adjunctive structure. Like, for example, you might have an application and the backend might have a primary database for consistency, like an RDS. It might have a DynamoDB database for really fast kind of like blob data that it needs to retrieve, like product descriptions and stuff like that. And then you might have a graph database, which might do the relationship and recommendation backing for the recommendation engines, because you can query relationships fast. And then you might have Elasticache in front of those caching complex queries. And then you have Redshift off to the side doing reporting for your application. So Adam, like Wikipedia, like in terms of like the relationships between the articles and all that, yes. But Wikipedia has content and significance around the relationships between the content as well. So it has like a little bit of both. I would think more around social media relationships, like who likes who's related to who spends time looking at whose articles, what products then to this class of people, this demographic like because we want to know the relationship between the characteristics of the demographic versus the product. I will be clear, recommenders are more likely to fall into a data science setup instead of crafting rules, which is what we do with code versus machine learning as an example. But you're headed in the right direction. It's about the relationship and not necessarily the data itself. That's a lot. Any questions about graph databases, cache databases, OLAP, analytical databases, or transactional databases? Okay. So now we're on to DynamoDB, and so this is the one we're going to switch over to. Fully managed system. It is serverless. You don't get to choose a t-shirt size server that then feeds your database like you do with RDS. This functions off of tables, and what you do is you just tell it how much capacity you want from reads and writes, or you tell it to auto scale. You put it on demand and just let it figure it out, right? Just I gotta tell you, DynamoDB used to be a real pain when you had to turn the dials on reads and writes. Since they released like auto scaling, whoo, you can set a min or a max if you want to do some limitations, or you can just let it go to town. Which I gotta tell you, that means when it's not doing anything, it sits at 0. When it's doing something, it can go up to your account limit, which is nice, right? 10,000. I think it's 10,000. So let's talk about DynamoDB's little tables and partitions and whatnot. Okay. DynamoDB stores data in tables, which is different than how RDS stores the data in a database engine that's sitting on an EC2 instance. So the reason is that this is completely serverless. And every time I say the word serverless, think hidden servers. But you don't get to see them at all. You don't even know they exist. You don't even know what's powering this thing. You know how many there are. But I want to be clear about this. Like, I want to say in like 2019 on Prime Day, a single table was handling 24 million transactions a second. That's a lot. Now remember, each row in here, row in data set, which is basically the key plus the attributes, cannot exceed 400K in size. So we're not talking about a massively large data retrieval system, right? But don't worry, you could put links into S3 or to other systems to retrieve more data, right? If you need to, or references to a database. But basically what happens is you create a table, you give the table a name, and then what happens is you say, look, the table is going to get split into multiple partitions based on the partition key value. Now the partition key value could be 1, 2, 3, 4. Like you could just do an ordinal kind of like setup, or you could do things like I want the partition key to be the name of a song artist. Now that would be an interesting key because you might end up with 500 songs where they're all keyed off the same, like Prince, for example, or The Weeknd or whoever, right? So then you kind of need to add like a sort key, which is the item in black. What that does is that allows you to basically sort based on the key that's in the black section right there. So your partition key is required. That's the green one. A sort key is not necessarily required. So a sort key can be used to define like how to store all the items within the same partition key. And you can order them by the sort key. So the sort key could be a timestamp. It could be the name of the album if we were going to make the partition key like the artist, for example. And a sort key is usually a one-to-many relationship based on the partition key. And it does enable querying along the sort key attribute. The sort key, by the way, is sometimes known as a range attribute as well, because they used to be called hash and range keys, but they're mainly called partition keys and sort keys now. Now, data is stored in partitions based on the partition key. So to mention this is that the more random that partition key is, the more likely you are to have your stuff distributed across a broad swath of servers. So one of the best practices, by the way, is to make sure that your partition key, has some randomness to it. I know, like, well, then how do we find it? We'll talk about it. Now, do note, by the way, that past the partition key and the sort key, you can put attributes in there. So for example, you could say, like, let's say it's the Weeknd, and let's say that's the partition key is the artist. Let's say that the sort key is the song title. Let's call it like I Can't Feel My Face, right? It's a pretty popular Weeknd song. Most people know that one. And then let's say the attributes are like the year, which could go in the first, and so you can just add attributes around the song and title, like what album was it on, that kind of thing. So you can add, by the way, any number of attributes as long as it's within that 400K limit for a single line item. So you can put as much text there as you want. And by the way, you don't have to fill in all the fields. This is a NoSQL system. So you do not actually have to fill out every attribute. You could have gaps in your data if you want to. It doesn't care. It's just going to blob that data out. It's a key value store. You give it the key, it returns all the values that are in the blob of data. So here's another example with some IoT data, right? There's a primary key here. It's a partition key. Notice it's got sensor A and sensor B. That's going to be very hard to find based on time. You know why? There's no time attribute. Where's the time data? Here, if you look at the sensor readings table, the sensor readings table has a sensor ID of a partition key of the sensor, and then you've got a time key. So in that way, you could say, look, for sensor A, I want you to return all the values that are between this time range, and it will give those values to you in order, right? So on the one on the left just has a partition key. The one on the right has a partition key and a sort key. So each item in the value section, regardless of the number of attributes in pink, the combination of the partition key and the sort key makes up the key, right? That's the key. So each item is uniquely identified by in a sense, the composite keys, the combination of those two keys. So you got to remember that DynamoDB can be used both as a key value store and as a document store. So everything that constitutes everything in pink, those are all attributes that can get returned. Now, in this case, our primary key is an item number, and there's attributes like title, lead actor, price, and circulation. Because an item, which is like what the row is, that's just a collection of attributes. Items are very like analogous to rows, and attributes are analogous to columns. So your row, by the way, cannot exceed 400K. Each attribute, by the way, in pink has basically a name, a data type, and a value, right? And attributes, by the way, can have like numbers, strings, binary, Boolean values like true and false. You can have it set null. You could have a string set or a number set or a binary set in there as well. You could have a lists or maps can also be done in there. You can also store like any JSON formatted document as an item in DynamoDB. So again, a reminder, an item, which is just a row, the maximum size is 400K kilobytes, not kilobits, obviously kilobytes. We're talking about data. Notice here that they've got a map in the document item. They've got a list in the document item. That can all be stored inside of DynamoDB. So remember, you got a table. Table has to have a primary key, a partition key. Optionally, it can have a sort key. The two of those together could form a composite key. And then you have n number of attributes. What did I say was the maximum length of a single item? What's the maximum amount of data, for example, you can store in a single row? What did I say that was? Good. Yeah. Good. Make sure you remember that. 400 kilobytes. Because they are going to ask you about that. Okay. Now, DynamoDB, by the way, is going to automatically, without you asking it to, maintain multiple copies of your data in AWS's regional data centers. So DynamoDB operates at a regional level and is managed at a regional level, which is different than like S3, which operates at a regional level and is managed at a global level because it has global attributes. It's different from DNS, which is a global service managed at a global level, right? Different from IAM, which is a global service managed at a global level, right? So DynamoDB operates at a regional level. So you can have tables with the same names in all your regions if you want to. Before you ask, DynamoDB, by the way, does support global tables. So was there a question? I think I heard somebody about to talk.
Yeah, I have a question.
Go ahead.
Could you go back to the document JSON? Yeah, there. So you're saying that, excuse me, that each row basically has to have 400K. So if this document is not necessarily spanning a row, but it's like a blob, I guess, in there. So now the document itself has to be 400K. Or what? I'm not seeing the visual of this in my mind.
So the aggregate of all the data that's captured in this entire row has to be less than 400 kilobytes, like 400 kilobytes or less.
So it could be individual columns or just this document size, basically.
Yeah, because like it's good that they put a JSON document up because as you can see, this is an attribute. This is an attribute. This is an attribute. This whole thing is an attribute. This whole thing is an attribute because that's a map and that's a list, right? That can fit actually in a single attribute column. The titles plus the actual data, if you were to put those all in JSON, they cannot exceed 400K. Just the characters.
Okay. Okay, I think I got it.
Yeah. So just for that row, right? Just that single row can't exceed 400K.
So in this, then you can have a mix and match of, title, author, price. Let's say on one row, and then the next row you have a JSON document, and the next row you have more attributes, title, lead actor, price.
Well, and in a sense, just so you know, it's from my perspective, it's all pretty much stored in JSON, right? So it all gets converted to JSON in some form or fashion. But yeah, like the total sum of all those characters when added together cannot exceed 400 kilobytes.
Okay. All right.
And by the way, you can stick binary sets in here, which is not recommended. Obviously, all of that in aggregate for a single row could not exceed the 400 kilobyte limit. Am I understanding your question, Gerald? I just want to make sure.
Okay, they said it all gets converted to JSON in the back end anyways.
Pretty much.
So, all right. I'll do some fine-tune reading on that.
All right, let me clear these out. Okay, so as far as like DynamoDB, like the table itself, because it maintains multiple copies of your data, they're usually consistent within about a second after you write to the table. So it's because it's got eventual consistency, right? So if AWS is maintaining 3 copies of your data, which is typical, within about a second of you writing, it's going to be consistent. Now you can specify the desired consistency when you read the data. So for example, you can say, look, I want strong consistency. And so think of it this way. Let's say that you've got 3 DynamoDB tables and you come in and you decide that you're going to change, like you're going to write some data here. And immediately you decide that you're going to come over here and you want to read that data. Oops, let's erase that one because that's not what I meant to choose there. Let's say you're going to erase that data. I'm sorry, you're going to read that data. Now, if you take what's called a eventually consistent read, which is, I believe that's the default, if I remember correctly, is that if you say I want an eventually consistent read, what's going to happen is it's going to return back to you this like previous answer because it's just going to take whatever's in this database. That's an eventually consistent read, meaning like I just want you to just return the value to me that you got, right? I don't really care. But if you're like, hey, you know what? I actually want a strongly consistent read. What's going to happen is that it's instead of just trusting that this system alone has everything that you need, this box that you're running the read query against, it's actually going to go talk to this one and say, hey, by the way, does anybody have any rights for this data value in flight? And it's going to say, oh, well, I do. And what will happen is then it's going to return this value back to the read because it asks for a strongly consistent read. But what's going to happen is that it's going to return the most up-to-date data. If something, by the way, is in flight changing this, it's not going to like wait for the write to finish. It's just going to return whatever it already has in red. With a transactional, what's going to happen is that a transactional is going to see that there's a write in process, and it's going to return the latest data, and it's going to wait for that write to finish. So transactional like makes it more like a database read instead of a like strongly consistent or an eventually consistent read like you would find with NoSQL. So you can make this run like a database by forcing both transactional writes and transactional reads. Sorry, go ahead.
No worries. Hey, sorry, I think I missed. What is the relationship between the 3 green databases?
There, Amazon runs 3 copies invisibly to you on the back end on your data. Like think of these as 3 different partitions of your data.
Okay, thank you.
Yeah, so when you run a table, even though it looks like you're writing to one entity, Amazon has it copied over 3 different times, both for performance, but also high availability reasons as well. And they can do that because it's NoSQL, right? That's the way most NoSQL systems work, is you're going to have multiple nodes in a cluster. They just happen to be doing it for you on the back end by default. And by the way, it could be 3, it could be 20, it could be 100. If depending on the amount of data you have in that table, you could be spread across 100 boxes, right? So just know that they're going to maintain at least 3 copies of your data at any given time. So the point to all that drawing was just to show that if you decide to do eventual consistency, then you could miss any in-flight changes. If you're doing strongly consistent, you could still miss any in-flight changes, but you're going to get consensus from all the systems that this is the latest value. With transactional, if someone's doing a transactional write and you ask for a transactional read, it is going to make sure that that transactional write finishes before it gives you back the latest update. But that's only true if there's a transactional write in process, okay? So make sure that's clear. Because remember, a transactional write is usually going to lock or imply, and it's a little different with NoSQL, but it's going to say, hey, I want you to lock this data while I'm writing to it. don't feed out any reads until I finish, which is what traditional RDS databases do. A standard write, by the way, is going to be eventually consistent. So it's going to take about a second for it to replicate. Does that make sense to everybody? Based on the 3 little partitions I had before? You ever get into a deadlock situation? If so, how do I best address that in code? What do you mean by deadlock, Billy?
Meaning that job 1 is writing table A, reading table B. Job 2 is doing the opposite, and neither one can proceed because they need to wait on the other.
Well, somebody got there first, right? So I'm not saying there won't be waiting, right? But they won't be deadlocked, right?
Okay, thank you.
Yeah, right. Somebody got there first, and so that's how that would work. So, in other words, if someone got to the data on one of the servers first, and then another one comes in like a millisecond later, and they're both writing to the same data, but this guy's got a millisecond timestamp, there's always a discrepancy. And what will happen is that on the back end, because I've actually asked this question before to the DynamoDB team, there's actually when that kind of situation occurs, which is super rare, the primary system will take ownership and they'll kick an arrow back to the second system and say, look, you guys came in at the exact same time. This was the primary. Please try your write again, right? So,
okay, thank you.
But that is super rare. Just to say this, like out of trillions of transactions, it's really hard to get them to do that at the same data block in the same millisecond. So, yeah. All right. Okay. So now remember, when you do your reads and your writes, you either can take the default, which is eventual consistency, or you can request either strong consistency or transactional. If it's writes, obviously you can only do the standard, which is eventual consistency or transactional. The reason this is significant is that this will determine or affect how your capacity is spent, right? So the read and write capacity units, and this is something that shows up on the exam, is that you're up to 4K in size when you write a single capacity unit, one action. Well, you can write 4K. I apologize. You can read 4K, you can write 1K. It even says it right there, and I'm not even looking at it. Right? So note that if you use eventually consistent reads, you're only going to use half of the capacity, which means you get 2 eventually consistent reads for that single RCU. Let me give you an example. Let's say you set your read capacity to 100 units per second, and you set your write capacity to 100 units per second. That means you can write 100 strongly consistent reads per second. Like you can read like 100% consistent reads per second. If you write, you can write 100 eventually consistent reads per second. In other words, what the number of capacity units that you use is dependent on the type of read you're doing or the type of write you're doing. But standard is that a read capacity unit is actually built for strongly consistent reads. So it's a 1-to-1 relationship. So if you do 1 strongly consistent read per second, you're going to eat 1 read capacity unit. If you do 2 eventually consistent reads per second, you're going to eat 1 read capacity unit. So it's interesting because eventually consistent reads can operate basically at double the speed of a strongly consistent read. Transactional reads operate at half the speed of a transactional. So it's like really fascinating because it's like you get double the speed if you use an eventually consistent read, but the cost is strong consistency, which is not good for financial transactions or something that's being updated frequently, like stock trading information. But note, first of all, that if you have 1 read capacity unit, it's going to allow you to write read 4K of strongly consistent data. 1 write capacity unit is going to allow you to write 1K of data. So remember that a RCU is 4K per, a WCU is 1K per. So just remember the discrepancies there. Because what will happen is they're going to test you on the exam and say, hey, you need to write. So this is a good question. If you needed to write 15, notice I said write 15K of data per second, how many write capacity units do you need? You need to write 15K of data. How many write capacity units do you need? 15, right? Because it's a one-to-one relationship. If you want to write 1K of data, you need one capacity unit. Now, if I want to read 15K of data, same data size. If I want to read what I just wrote, how many read capacity units do I need if I'm doing a strongly consistent read? That's right, because I need to eat 4, 4, and 4 to get to 12, and then I need to eat a 3 to get to 15, but they only give it to you in capacities of 4, so I need 16. I need basically 4 read capacity units at a strongly consistent read to make that happen. Now, if I want to read 15K and I'm using eventually consistent reads, how many RCUs do I need? Well, remember, eventually consistent reads, I get double the capacity. So I only need 2 versus 4. I only need 2. Remember, eventually consistent reads run faster than strongly consistent reads. So I only need half the capacity to do the same work. Because it's not going to go talk to all the backend systems. It's just going to talk to the one that's in front of it. Oh, don't worry. There's more on that. So I'm going to move on. But don't worry, we're going to come back to that math because you're going to see it again. Okay. Right now, the main thing you need to remember is that a read capacity unit of 1 will get you 4K. A write capacity unit of 1 will get you 1K per second. And if you go higher up the chain from eventually consistent to strongly to transactional, you're going to lose half of your capacity. You're going to lose half your capacity every time. Okay. We'll come back to that. Don't worry. This is on the practice exam, so make sure you understand the math, okay? Now, in addition to having read and write capacity per second that you can turn the dials on, and remember, I mentioned there was auto scaling here, so you can actually just set it to auto scaling, but you can set mins and maxes and say, this is how many reads per second I need for this table. This is how many writes per second I need for this table. You get to choose all those. In addition, you can actually set up indexes just like you can with a traditional database system. In other words, you can come in and say, look, I need to create what's either 2 types, a local secondary index or a global secondary index. Now, they allow you to basically query based on different alternate keys. So sometimes you can change the primary key, sometimes you can change the sort key, but it allows you to basically change the query structure that you're executing. There are 2 types. There's the global secondary index and the local secondary index. And I cannot emphasize this enough. Please make sure you hear what I'm about to say. You cannot create local secondary indexes after you've created the table. You cannot create local secondary indexes after you've created the table. They have to be created when you create the table. Global secondary indexes you can create all day long after you've made a table. They are going to trick you in the question several times and get it so like the answer is going to say, we'll just create a local secondary index and use your new query. And the answer is you can't do that. You can't create a local secondary index after the table's been created. You can create a new table, copy the data over, and at that new table you create a local secondary index. So just know local secondary indexes are considered to be local because they are typically located right next to your primary table. So remember, this is a copy of your table, but it'll have, for example, a different sort key. So let's take a look at this just to make sure that we're drawing this out really clearly. These partition keys match because this is a local secondary index. note that this traveler ID and this contact ID are different. Notice they've been swapped with their attributes. Okay. Billy, no, the tables are all independent. So a single item can't, remember, this is replicating data from the primary table. So this is a copy of your table. So yeah, it does, the same limits apply because it's copying the data from the primary table. So the 400K row limit applies here as well. Because it's just copying data from the primary table. So the only thing you've done here is you've changed whether you have sort keys or partition keys or whatnot, right? Like, in other words, your primary key is the same, your partition key is the same, but you've changed your sort key, right? So notice, by the way, that a local secondary index eats capacity from the primary table. So if you set this to 100 and you set this to 100, both the primary table up here and the local secondary index are going to eat out of that same capacity. In other words, the local secondary index does not have an independent engine from the primary table. They both use the same capacity. Now, local secondary indexes, by the way, will support eventual consistency and strong consistency, because remember, these are read-only tables for the most part, right? Why? Because it's getting its data from the primary table. You're going to write to the primary table. You're going to read from the local secondary index. This doesn't work any different than it does in a database. Indexes are for reading. You don't write to an index, right? You create indexes from tables that are being written to, but indexes themselves, you do not write to. So this is a local secondary index. It cannot be created except when the table is created, the primary table is created. It is a copy of the data in the primary table, but you can change the sort key. Capacity is the same. Now, this whole thing is a little different compared to what they call global secondary indexes, because global secondary indexes basically operate as an independent engine from the primary table. Notice here that the partition key has been changed in the global secondary index. It doesn't match the primary table. Notice also that this one doesn't, like, they've added a sort key in the secondary index, and global secondary indexes can be created at any time during a table's existence. They can also be deleted. They only support eventual consistency because, remember, they are an independent copy with their own engine separate from the primary table, and they have their own read and write capacity. So they have to talk back to the primary table, where with a global, like a local secondary index, which is the one we were just talking about, this local secondary index lives on the same physical piece of hardware as the primary table. The global secondary index doesn't. It lives on its own servers, but it has to go and talk to the primary table to keep its data up to date. So when you go back to the primary table and you change data, it gets replicated to the global secondary index. It will only return, by the way, attributes that are projected into the index. So you don't have to create a global secondary index that has all of the attributes of the primary table. You get to pick and choose what you want to put in the global secondary index. Let's see. Is there anything else to share about this? Billy, you were asking about, like, does the like row size change? No, it's still 400K. Here's something interesting though, is that the total size of the like local secondary index cannot exceed 10 gigabits, or sorry, 10 gigabytes. I don't know what's going on with me today. 10 gigabytes, just because it's co-located on the same partition. So they have a like a size limit there. You can change the sort key. I don't know that you have to project all of the attributes from the primary table into the local secondary index, but note that you do have to create the local secondary index at the time you create the table. So you cannot delete a local secondary index once it's created. That you don't have to use it, by the way. It can just sit there. But just know that you can't delete it. You have to delete the whole table, right? Global secondary indexes, by the way, since they operate independently and are created independently on a separate server, they can be deleted and added to. And by the way, they don't have a size limit. They can replicate whatever's going on with the primary table. Okay. When would you use global indexes? So you would use global indexes when you need to run a query that the primary table is not optimized for, and you need to change both the primary key and the sort key, right? You need to switch it up. The main reason you use indexes, and this is true by the way for our RDBMSs like RDS as well as DynamoDB, is you use indexes when your queries are not optimized against your tables. So if you put an index in front of it, which is basically a copy of the table that's been rearranged for the query, it allows your queries to run very efficiently and search for certain attributes. So you use local secondary indexes and global secondary indexes to optimize your data for querying, because you can't change necessarily the data that's on the primary table, but if you put it into an index, you can. So mainly it's for optimizing for search for queries. Notice I didn't say scans. Other things to note is that in addition to having a primary table that has its own read and write capacity unit, obviously, if you're doing strongly consistent reads, you're going to get 4K per unit on reads, 1K per unit on writes. In addition to having the possibility at creation time for the table of creating a local secondary index, which has the same partition key, but a different sort key, in addition to be able to, on the fly at any point in time, creating global secondary indexes that have whatever arrangement of partition keys and sort keys you want, you can also make it so that when an item is updated, it triggers a notification to what they call DynamoDB streams. This can be used to capture changes against a table, such as like, did the key change? Did an attribute change? Can we send both the old and the new data? In other words, you can log everything that happens. You can also use this to replicate data, send it to a Lambda function. You can do all kinds of stuff with this data, right? It's basically the ordered flow of change information about a table. So when you make an update to a table, DynamoDB first is going to durably persist the change, and then it's going to asynchronously update what they call the DynamoDB stream with the changes that are being made. The records in the stream are stored strictly in order, time order from when the changes occur, and a stream record is available for about 24 hours. This is technically dumping into a service called Kinesis, which is based on shards. So just know that if you're familiar with Kinesis, this is how this functions. It's important for you to know, by the way, that it's only going to keep data for about 24 hours. That does show up sometimes on the exam. You can also create global tables. Global tables are a little weird, by the way, because you have to create all the replica tables first and then have them join the global table. Each replica is going to store the same set of data items. I think you're only limited to one table per region. Every replica has the same name, the same primary key schema. And this is all eventual consistency, by the way. If you want strong consistency, you have to read and write to your local regional table, but it'll eventually get replicated to the others. So this is all eventual consistency. So it's not strong consistency. By the way, when I say strong consistency, let me clarify by what I mean by that. Strong consistency, when it relates to a write, is very similar to a transactional consistency. It means that when you write something to a system that has 3 nodes, when you write it to the first node, it immediately writes it to the second node, and then it tells the client that the write was successful. That's like a two-step kind of like write, if you will. It's also known as just strong synchronicity. Oh, wait, is that right? Strong synchronicity. Synchronous writes, not strong synchronicity. I'm not sure what I was referring to there. Synchronous writes, which means that you don't tell the client that the write was successful until every data store in your cluster knows that the write has been written to disk, right? So that's what a strongly consistent write is. It's where you're saying, hey, I'm writing this out to every member of the cluster. Everybody's accepted it. We've taken your write. Eventually consistent writes, if they existed, would basically be, hey, I wrote to this node. The node told me that it got the write, and then eventually it's going to replicate it out, right? That's the standard for writes, is it writes to one node, tells you that it took the write, but then it's going to take about less than a second to replicate it out to other nodes. That's an eventually consistent write. That's the standard, but that's not the same thing. So remember, global tables are different in the sense of that you are actually replicating data globally, so multi-region. So this is great because what it does is that one of the tables is actually going to, let's say we wrote data in this table over in side one. What it does is it's going to write to the stream, and then what will happen is that the stream is then going to replicate the data out to the other tables in other regions. Remember, this is eventually consistent, so this could take seconds to replicate. Now, speaking a little bit to Billy's kind of earlier question about like deadlocks, for example, conflicts can arise. They are rare, but they can arise where if you try to update an item at the same time in different regions. So Billy, your question would seem to be a little bit more focused about local, which that is rarely happens on a local table. That's like a 1 in a trillion kind of thing. But if you're using a global table, you can easily run into the problem you're talking about, because the system may not be aware at the time that writes are being made to the same thing. And they could, you know, again, time is usually the limiting factor, right? Last writer wins, basically, right? So whoever wrote first, their change happens. Whoever wrote last is the last change that happens, right? So what's interesting here is that notice it says that 11/21/03, someone wrote red in as a color. And then at 11/21/04, someone wrote green in as a color. So with this conflict mechanism, what's going to end up happening is that green is going to win because it was the last writer. Now, as you can imagine, what if you're doing financial data and someone added like 50 to the thing, and you're going in, you're adding 50 to the thing, but you think the previous number is this? The way you get around that, by the way, is you read the data first, pull it back, and then you do a conditional write. If the read equals 50, if the value in the thing equals 50, then go ahead and add 50. If it doesn't, then throw an error and check it again, right? So that's how you handle that in application logic, is that you set a conditional read where you read the data and say, oh, my bank balance is currently $1,100. And then when you go to do the write, you set a conditional write that says, if the bank balance is still $1,100, add 30 to it, right? Because that way, if someone comes in behind you and adds $100 in there, you're not going to overwrite their changes because they're also checking for conditional writes. But just know that by default, if you don't handle that in application logic with conditional writes, you have to handle it. You have to just be aware that the last writer is going to win. But I got to tell you, financial data changes that whole thing. So just know that with local tables and with global tables, last writer wins. If you're worried about that from an application logic standpoint, use conditional writes where you pull the value and only write if the value equals what you pulled. If it doesn't equal what you pull it again, right? So have them retry the operation. Billy, I hope that clarified that finally, because I knew we were going to get here eventually. All right, Adam, you may miss this, but once you select a write consistency, can you modify it later? Or do you have to recreate it? Oh, no. Adam, sorry. Consistency is based on a per transaction basis. So you can change it at any time if you want to. The table replication methodology can't be changed. Like you can't force the table to replicate strongly consistent because of the distances involved. It's always going to be eventually consistent replication for the tables. As far as your transactions go, though, you can make one, you can make the first one eventually consistent, make the second one strongly consistent, make the third one transactional. You can control at an individual level how every single read or write is executed, right? Just remember though, with writes, there's only eventual consistency, which is the default, or transactional writes, right? So remember, there's 3 levels in reads. There's only 2 levels in writes. So make sure we're clear on that. All right, so this is how like concurrent writes are basically resolved, right? Hello, there we go. All right, wrote out read consistency for a global table, right? So remember, if you want strong consistency and you're using a global table, then you need to stick with your local table, not write necessarily to like a table in another region. You're gonna do all your reads and writes to your local table. If you don't care where you pull it from, because the data it's okay if the data is like slightly inconsistent because it's not updated very often, then you can pull from whatever table you want. Just remember that if you write to US East 1, the data is going to be eventually consistent in US West 2. So the general recommendation is that if you're using global tables with DynamoDB, just read and write to the table that's local to your region. Don't use the table in another region. That's just silly. I don't even know why you would do that to begin with, but maybe if the table was down, which would be weird, you might go to another system, but that should be a worst case scenario. In general, your application should read and write to the local copy of the global table that's in the same region as the application. Do not write to services that are outside of your region. That's a recipe for disaster. Okay. I know most of you are like, Michael, what would be the use case for that anyway? DR. So I don't suspect that by default, most people would intuitively do that, but just in case, you now know, write to the table that's local to your application. Let's see. Oh, so creating a table, which by the way, this does come up on the exam. First of all, you have to create an ordinary DynamoDB table with streams enabled in the region that you want. And then repeat that step for every other region that you want this table to be replicated in. And then you have to go in and define a global table, and you have to include all of the tables that you just created. I don't know why they ask you this, because it's like not like you couldn't look this up, but they do ask you. They're going to try and trick you and say, create your global table first and then create your local tables and blah, blah, blah. No, create local tables, enable streams, repeat that, create your global table. That forces them all to replicate with each other. This is on the exam. Other things to know outside of global tables, outside of local secondary indexes, outside of global secondary indexes, outside of read and write capacity units, is backup and restore. So DynamoDB has basically on-demand backup and restore capabilities. So you can take full backups for long-term retention, for regulatory compliance. There's a service called AWS Backup that will allow you to set this up, schedule it automatically. You can do it with a single click or a single API call. Has zero impact on table performance or availability. If you create an on-demand backup, by the way, it's created asynchronously. And by the way, if you do a restore, just know that you can do like point in time recovery. So like, for example, if you need to, you like a test script accidentally writes to like a production database. With point in time recovery, you can restore that table to any point in time during the last 35 days. So DynamoDB, by the way, is going to maintain incremental backups of your table for you. So you can point in time recover it anytime in the last 35 days automatically. Okay. Which is kind of nice. Have used that many a times, actually. Obviously, so since this is serverless, DynamoDB, by the way, is fully integrated with IAM because it's not a separate system. It's integrated in with AWS. So you can, there are control operations, there are data operations. There's also stream operations. I'm not sure that am I missing something? There should be stream operations listed here, which allows you to control like the DynamoDB stream. So there's like, it lets you enable, disable streams and data modification records. Your control operations are about what you can do to manage the tables. Your data operations are like CRUD, you know, create, read, update, and delete, right? So, yeah, kind of interested as to why they didn't put streams here. Just note that there is an object persistence model. I think it only works in Java and .NET. Oh, never mind. It says in the lower hand side, available in Java and .NET. So the object persistence model basically will allow you to do CRUD operations, run queries, because it basically allows you to map client-side classes to DynamoDB tables. And so the instances of these classes, these objects, map to items in the table itself. So you can use this objects persistence model, this programming interface, to connect to DynamoDB, do CRUD. You can even do optimistic locking if you want to with the version number. You know, and again, this is only supported in .NET and Java. So it's not in Python. Let's do this, by the way. We've been going at it for about an hour and 45 minutes. So it's probably like a good time to take a break. So it's 10:15 right now. Let's take a 20-minute break if it's okay. And let's come back at 10:35. So 20 minutes. We're gonna take a 20-minute break, okay? All right. We'll hear you in just a second. All right, any questions about read capacity units, write capacity units, local secondary indexes, global secondary indexes, what they do, any numbers there, global tables, streams? Okay. Let's talk about creating a table. Well, it's not that hard. The DynamoDB console is a little different from the other consoles, a little more data focused. Basically, you just create the table in question. It is going to ask you if you want a sort key, which, you know, you can set it to whatever data type you want to use. I don't think it can be a list or a map, but string, number, etc. At the time, remember that you have to create the local secondary index at the time you create the table. Globals can be added at any time. Streams can be able to at any time. But the LSI, the local, has to be created at table creation time. Now, in addition, once you've created the table, you've got a bunch of tabs that you can click on, such as being able to see the items, get metrics, see alarms, like capacity. There's a bunch here. Indexes. If you have global tables, if you have backups, triggers for your tables, there are a lot of options for DynamoDB. Do you need to know them all? No. No, you don't. Not at this level, right? When you decide to go for the database specialty, then you'll need to know all the options. But for this one, you do not actually. Okay. Now, when you create a table using the API, you might notice that, you know, you just basically, like, this is Python, obviously. You invoke the resource, create the table, set the attribute names. Remember, you actually have to have a hash key, also known as a partition key. You do not have to have a range key, also known as a sort key. So it is going to do it in an asynchronous manner. You do set things like write capacity, LSIs, GSIs, settings for server-side encryption, all that stuff can be set here as well. Now, You can turn on what I mentioned before. Instead of specifying your read and write capacity, you can do on-demand capacity. So what this is, it's a flexible billing option, which can allow you to serve like thousands of requests per second without doing any capacity planning. So when you choose on-demand mode, what happens is DynamoDB just ramps up the RCUs and WCUs to reach any like per level of traffic. So you can choose on-demand for both new and existing tables. You don't really have to like change anything, right? If you create new tables and you have an unknown workload, this is a great option. If you have unpredictable application traffic, if you only want to pay for what you use, I mean, the request rate limit, by the way, is whatever your account is set to, the upper limit. And the minimum can also be set if you want to set it to provisions. So. Now we're going to talk about the different actions you can execute. For example, you can put an item, which is just, putting the item in there, right? You can relate. By the way, put will replace an old item with a new item. If it has the same, by the way, primary like partition and sort keys, it's just going to override it. You can actually ask to have no return values, that which is the default value, or if you overwrite something. If it's not a new item, you can just say, I want all of the old stuff. The content of the old item could be returned to you as well. So reading an item is the same thing. By the way, since put is a write, right? Technically, you can control basically how you write this out. In other words, you could say, I want to do standard default, which is eventual consistency, or you could say transactional. Get item has the same thing where you're just like basically reading an item. You need to obviously specify the table, the key, any like projection expressions. So you can actually say what attributes you want to retrieve from the table that match this particular key. You can set the read consistency. If consistent read is set to true, it's going to use strongly consistent reads, but by default, it's going to use eventually consistent reads. So updating an item, adds an existing item's attributes or adds a new item if it doesn't already exist. So it's interesting that put and update can both be used to update an item. That's not necessarily unusual. Elasticsearch does that a lot too. Deleting an item, same thing, right? You can also get return values. Return values here, by the way, could be nothing. Like I don't want any return value. I want all of the old, the updated old, all the new, like all the updated new. Like if there's any changes, you can actually just get tons of return values here. You can, by the way, put conditional expressions for your deletes. You can also put conditional expressions for your puts as well. So this is the one where you could say, look, I'm going to retrieve the value because I'm doing financial information. It's $50. I'm going to add 50, but only if the value is still 50. So you can put conditional writes in as well to the put item and to the delete item piece. I don't think, I mean, there's no reason to put conditions in for a get item. I don't think that update item has a conditional. All right, so you got your standard CRUD. You're basically your put, your get, your updates, and your deletes. And then you can also like query a table. So the query operation is going to read from a table or a secondary index only the items that match the specific key. It's then going to like further refine the output using a filter expression. You have to explicitly set the table or the secondary index you want to query. And you can also determine consistency here when you query a table. You can say, look, I only want strong consistency. I want eventually consistent. In this case, this is using the Python query method against the table, where basically you retrieve all the items that are in the user table, where the key is username, right, equal to John Doe. So it's basically looking for where the partition key is equal to John Doe. Here, where you're scanning a table, so query is actually looking for a specific item, so it queries the partition and returns the thing. Scan is similar to query, except the scan is going to read all of the items from the table or index. This can also be filtered, by the way, by a filter expression. In this particular case, it is reading the entire table along the attribute age where the value is less than 27. This is an expensive operation. So on the exam, if it asks you to use a cheaper query type, or like a cheaper way of retrieving information from a table, they're going to focus on you using a query over a scan, since the scan is a less efficient operation. You can, by the way, set things like to have it do a parallel scan where it runs the scan in parallel and then brings the aggregated results back to you. But just know that this is true with RDBMSs as well. A query is more efficient than a full read of an entire table. Now, they do have this context of an expression attribute. It's basically a placeholder that you can use in an expression. So, and it's an alternative to an actual attribute name. So an expression attribute name, which is like this alias, right, to an actual attribute name, it's got to begin with a $sign followed by like one alphabetic character and usually like more alphanumerics. You might use an expression attribute name when you have named an attribute that conflicts with a DynamoDB reserved word like backup, as an example, right? In other words, you might name an attribute backup, but you can't run any queries against backup because that word is reserved by DynamoDB. You could then set up an expression attribute name that aliases, pound B has an alias for backup, and then you can put that in your queries, right? So you can actually like search for it. So you could also do this, by the way, when you don't want to basically, if you don't want to like have literal values in, you want to do some kind of substitution, interpolation. My brain's not working. These expression attribute values, which are different from expression attribute names, these literally start usually with a colon, right? So that way you can use this as a placeholder when you do not want to hard code literal values into your code. I would say this, so we usually handle this in other ways inside of like Python, for example. I don't really know that we use these a whole lot. I don't know that I would ever name an attribute after a reserved word. I don't really do that. If I find there's a conflict, I just use, I just use something like a variable inside of Python instead. But if I find that an attribute name conflicts with a reserved word, I just rename the attribute. I don't want to deal with having to do like substitution just because I'm attached to a particular name. Let's see, what did I say there, Antonio? So the names start with a $, the values start with a colon. Oh, sorry. Yeah, did I say that wrong? So this is for names, and this is for values. Good. I think I may have mentioned this before. In addition to being able to do substitution or aliases, which is what the basically the previous slide was all about, was basically the expression attribute names and expression attribute values. You can also do what are known as conditional writes, right? And by the way, that conditional write could be an evaluation of the current value plus an additional value. Like here, for example, they're only going to basically set the account to locked equals no if the current login time is greater than the last login time plus 24 hours. So a condition parameter is a condition that has to be satisfied before a write operation is to be performed. This applies to puts in DynamoDB and deletes in DynamoDB. So you can specify conditions for that. You also can limit the amount of table data that's returned. So when you do a query or a scan against an entire DynamoDB table, the results are divided into pages that are about 1 megabyte in size or less. That way an application can, return the first page of results and the second page. So a single query is only going to return a result set that fits within a 1 megabyte limit. So the default pagination limit is actually 1 megabyte. Now you could also just say, look, I want to limit the number of results, right? And say, I want to like scope it and say, look, just return, the first 100 lines or 2 megs of results. So just know that limit will trump pagination. So if it hits limit first, it's going to run the limit, stop the operation, and return all the matching values at that point. And then you can use, by the way, what's called this last evaluated key parameter to like figure out what the next page or what's next set of results should be. This allows you to pick up where you left off, because maybe you're displaying one page at a time. And by using the last evaluated key parameter in DynamoDB, and you can see it there listed as the bottom, this allows you to display the next page because it'll show you the last evaluated key. By the way, you can also choose an arbitrary start key and just say, hey, like I want to start, 100 lines in. That's the exclusive start key. So you get control where you start, where you end, how much pagination you display, how much is in those pages, etc. You also have batch operations, which are usually more efficient than single operations. Batch get and batch write, by the way, you can actually bundle up to 100 items that can amass up to 16 gigs or 25, puts or deletes, right? Again, also up to 16 megs of data. If one of the requests in the batch, either of the 100 or the 25 fails, what will happen is the entire operation isn't going to fail. What's going to happen is that in the unprocessed items, they're going to return that to you for querying. So you can actually query unprocessed items and see what wasn't done. And then you can just reprocess those unprocessed items. If you keep failing with them, you can actually push them to the side, like take them out and say, hey, let's take a look at these. Let's write these out to an error log or send a notification or some variation thereof. So this is for batch, like in mass write and read operations. Now, transactional operations, which, notice that this is introduced so you can handle transactions. What this will do is that this contains a set of items that you're going to write. It's going to contain a read set. And by the way, this can happen across multiple tables if you want to. Conditionals will also apply here. So if you only want it to write based on certain conditions, you can do that as well. Just to say this, you have to plan for additional reads or writes when you use transact, because DynamoDB is going to do 2 underlying reads or 2 underlying writes of every item that you use these 2 methods with. So it's like one write to prepare the write and another write to commit the write. One read to get the item, to prepare for get item, and one read to actually do the get item. So each transaction, by the way, will, about one transaction a second, for example, you're going to require 2 capacity units for each of those transactions. So if you were going to run, for example, 3 transact write items, you're going to need 6 capacity units to actually do that. So do note that the default behavior is that if one of the operations fails inside the transaction, the whole thing fails. The default SDK behavior is to retry the transactions in case that there was an exception. You need to do some planning for, by the way, for these retries. So just something to be aware of. Transacting against DynamoDB requires a little bit more planning than normal, because you have to account for the double capacity unit consumption, and you have to account for the fact that there's going to be retries. So all right, last few things. One, remember that I said before that you really want your partition keys, right, to be non-sequential. so that Amazon will spread them across like a large amount of servers instead of having them all sit on the same server. If you are using a sequential number like 1, 2, 3, 4, 5, like that's Amazon is gonna hash that and just stick it all in the same backend box. You really want to get Amazon to scatter it across a wide number of systems. And so that's, they usually recommend using some kind of random hash prefix for at least the beginning of your key. You could, for example, filter that out if you need to do that in code. And you can, by the way, do that by calculating a suffix. So you could have a 1 dash and then a random hash, a 2 dash, or some variation thereof. I guess the bottom line is that make sure that your partition key is not just an ordinal or numerical linear kind of like progression. Try to put some differentiation inside of your partition keys. A lot of people will create a table per day or a table per week or a table per month because they'll rotate out older data, right? So they'll still keep the older tables around, but they might export them and put them into Redshift, or they might write them out to a flat file inside of S3. So just know that way, if you do that, you can keep your provision throughput high on systems that require it and low on data that's not going to be accessed. Plus, it'll make your queries and whatnot more efficient because the data set's going to be smaller. If your table has items that store a large number of values in an attribute of like a set type, such as a string set or a number set, considering removing the set attribute from the table and splitting it into separate items like on another table. In other words, have that attribute refer to the other table in order to get that set of items instead of creating like a nested array, right, inside of a system. This is true for most systems, but nested data structures inside of nested data structures causes all kinds of slowdown. I've particularly seen this a lot, for example, with NoSQL systems like Elasticsearch, but it's true here as well, right? For example, if you have a table that stores threads in a forum, right, and replies as a string set in each item, each of those items can actually be pretty large, like approaching the over and above the 400K limit inside of DynamoDB. Throughput's going to be reduced because you're going to be fetching unnecessarily large amounts of data when all you really needed was the thread subject, right? So for example, how do I cook potatoes, right? So instead, you could actually have a simple forum thread, which has the thread ID plus the subject, and then all the replies could actually be in a separate table. So, ways to approach that. Possibly, yeah, Gerald. I mean, that definitely applies. I mean, because there is a foreign key, right? The thread ID of 1, 2, 3 is actually in both places, right? So one links the other. So not a bad analogy. Store frequently accessed small attributes in a separate table. I think we talked about that just now. It's like a variation, right? Is that instead of storing a bunch of small attributes in the primary table, just refer to it as another table, especially if they're not queried a whole lot. If the data is not being accessed, consider moving it off to another table, right? Just let it stay there. Because you might have a primary table that's used for referencing and indexing, and then frequently changed data would go to one table, and frequently changing table might go to another table. Like data that doesn't frequently change they might go into different table sets with different read and write capacity units. Now, with local and secondary indexes, one of the best practices is try to use them sparingly, keep the size of the index as small as possible. Create local secondary indexes only on attributes that you are actually going to query. So for GSIs, make sure you choose a key that's going to represent a uniform workload. Obviously, same thing. Make sure you're sparse with your index. Don't project everything in the primary table up to the global secondary index, especially if you're not running queries against it, right? So create it with a subset of the table's attributes for specific queries inside your application. You can create up to 20 global secondary indexes against the table. So there's no reason not to be judicious with this. It's not going to cost you anything other than storage, which, that could get costly. Typically storage though is cheap. So just be mindful of that. And then you can, by the way, like add a version number has an attribute into your table, right? So like you can use optimistic locking with the version number to make sure the item hasn't changed since you last saw it, right? So, this is also known as like the read, modify, write pattern or optimistic concurrency. But it basically says like, I'm not going to write to this particular attribute if like this version number hasn't changed or if the attribute has changed since I last saw it. So optimistic concurrency, where you're not necessarily locking the table, but you're saying, hey, if I go to write this out and it's not the same value that I just read, it means somebody changed it. So let me read it again. And especially when you're doing incremental changes, that's really necessary. Let me just check on something really quick. Okay, good. Just want to make sure they're still warmed up. All right, outside of optimistic concurrency, the last couple things we're going to talk about is this. Just know that DynamoDB has a read-only accelerator, like a read-only like caching accelerator called DAX, DynamoDB Accelerator. This is an in-memory cache that will reduce your response times from milliseconds to microseconds. So this is for read-heavy or bursty workloads. DAX is going to increase your throughput and potential savings to like, it's going to reduce the need for over provisioning read capacity units. So DAX is a read through, write through cache. So when a read is issued to DAX, it's going to check to see if the item's in cache. If it is, DAX is going to return what it has. If it's not, DAX is going to fetch the item and then automatically present it for subsequent reads. For writes, DAX first writes the value to DynamoDB, then caches the value in DAX, and then returns success to the application. So it does a synchronous write through for writes. So this is an accelerator. This is what they use when they want to get from milliseconds to microseconds. So any questions about the put, one-to-many, hot and cold, uniform, transactional operations, anything that we just covered around DynamoDB and how to basically put items, get items, update items, delete items, conduct transactions, anything there?
I have a question. A lot of times with relational databases, nulls create a lot of problems. Do you have that concept with DynamoDB or not?
Sorry, what creates a lot of problems?
The concept of a null value, meaning that field doesn't have a value and it's handled separately.
Yeah. So DynamoDB does have null values, but they don't care if an attribute has a value. So you don't have that same problem in most NoSQL systems because null in a sense is a value, right? It's a value of nothing, yes. Right? Like NoSQL databases like DynamoDB don't even care if there's anything there. It doesn't even have to be defined.
Is there a way to force a column to not accept? I'm sorry, to force a column to have a value other than have an index possibly?
You do not. This is a schemaless flexible system, so you cannot force a column to have a value. It is not. It's not a requirement. The column doesn't even have to. The attribute doesn't even have to exist inside of the system for every row. If that makes any sense.
Yes. Thank you.
Yeah. It's very different. That is a big problem with RDBMSs, and it doesn't exist inside of NoSQL systems typically. All right, here's some general troubleshooting. First of all, if you get an error back from AWS, you should probably do something with it. Does that sound like common sense? If you get an error back, you should probably, if it says unprocessed items or we're throttling the table because we're out of read capacity units, the SDK, like there's known use cases for how to respond to that. In some cases, by the way, the SDK will like retry and do exponential back off and stuff like that. So you need to read your documentation to understand, but like you want to know how your application is going to handle that, right? Obviously, you can log every single API call made against DynamoDB through the security mechanism of CloudTrail. And you're like, well, wouldn't that give you some performance metrics? Yeah. So yeah, but mainly CloudWatch is going to be where you're going to get your performance metrics, right? Because that's what CloudWatch is for. Obviously, if it's a 400, like, what is the error telling you? Is it malformed? Did the item not meet a conditional? Like, what was the issue there, right? For others, like 500s, an example, like 500s and 503s are going to have to be resolved by Amazon. So you can retry until the request exceeds. But any other error, by the way, you're typically going to retry, or you might put logic in there that says, hey, if the provision throughput was exceeded, increase it by 10 and try it again. Increase it by 10 and try it again. I know some people who've done that, but honestly, just turn on demand at that point if you're going to do that. Why force yourself to have to manage that at a code level? Just turn on demand for that. And I think I talked about 500s and 503s already. Now, when it comes to batch operations, right? The SDK, by the way, is going to give you, it's going to retry automatically. And it's going to use exponential backoff and retry failed tables and blah, blah, blah. But you are going to have to like get information from process keys and from unprocessed items if you want to see what actually has failed. So when you get things like provision throughput exceeded exception, that means that you've run out of horsepower on your table. Now, you can set up a CloudWatch alarm that notifies you when a table exceeds 80% of its threshold. You can even set up an event in response to that alarm that like triggers the table to scale, or you can turn on demand, which does the exact same thing. So, or you can write your own if you want to. Either way is fine. Much like with any data store, how you query and how your system is set up to receive and optimize those queries is an art form. I know that being a database administrator is not cool anymore, because now it's just like system admins. We're all being called, SREs, and database administrators are now being called data scientists and data engineers. It's great. I have no problem with the name change. The issue is that it still requires the same skill set. You can't just query an application 50 different ways and not optimize the data store to take the query. Doesn't matter if it's DynamoDB, doesn't matter if it's an RDBMS. You still actually have to learn the science and the art of executing your queries and how to make the system fast for those queries. Still present today. Okay. Now, in our core scenario where we had like website hosting, we're using S3, and we had like video and image hosting using MP3s, audio files. What if we wanted to throw a data store into the equation, right, in order to build our application? This is from our very first slide deck, right? What does that look like? Well, I just want you to know that our lab, this is why we're going to have you build DynamoDB up to kind of like get that going. Now, I'm going to do the knowledge check, which is the very next thing, but I want all of you to do me a favor. And I know this is going to sound weird, but just trust me for a second. I want you to log in to webage.quicklabs.com. I just lost some labs. That's weird. I want you to open up webage.quicklabs.com, and I want you to go ahead and click on Start Lab just to get that thing rolling, just to make sure that it provisions correctly. Because I don't know if you noticed, but there were 25 labs ready, and now I saw it drop down to 19 just now, so I'm a little weirded by that. Okay, so go ahead and open your lab, and go ahead and click on Start Lab for this developing NoSQL solutions for DynamoDB. And then I'm going to do the knowledge query while it's doing provisioning. I just want to make sure that a minimum number of you are waiting for it to do that. Okay, just a little concerned about its behavior recently. All right. Don't worry, you have plenty of time on that timer. If you take all that time, we're never going to get to lunch. All right, so Amazon DynamoDB is a fast and flexible relational database service for applications. Is that true or false? That's false. Dead on. Okay. A global table is a collection of one or more DynamoDB tables, all owned by a single AWS account, identified as replica tables. Is that a true description of how global tables work, or is that false? Because remember, with a global table, you first create all of the like replica tables first, and then you make them with streaming enabled, and then you make them a member of the global table, and they're all owned by a single account, actually. So that's true. Yeah, right? What may have thrown you off is, I don't know how many times I said the word replica table. It could have been 0, but they are considered replica tables. So number 3 is, if you want to perform queries on attributes that are not part of the table's primary key, you can create a global secondary index. Is that true? Can I change the primary key in a global secondary index? Is that true or false? Yeah, that's actually true. Now, if that said local secondary index, you can't change the primary key on a local secondary index. You can't change the partition key. So, but with GSIs, you can. So that's true. All right. So RCUs are the number of strongly consistent reads per second of items that are up to 2K in size. Is that accurate for RCUs? Well, the funny thing is that remember, RCUs are how big in size? Well, they're 4K. So that's not going to cut it, because that's a 2K in size, right? And it is actually strongly consistent reads at 4K in size. If those were eventually consistent reads, you get 2 of them for every strongly consistent read. So it actually would be 2 4Ks, right? That's good. It's false. All right, to achieve maximum read and write throughput, choose the partition key carefully to avoid hotspots. Was that a best practice to make sure that you are like crafting your partition key to avoid hotspots? Was that true or false? Yeah. If you want maximum read and write throughput from your backend table, you're going to need to at least append or suffix a hash, a random hash. It could be 1 underscore blah, 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 2 underscore blah, 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 random hash, right? That way, when it hashes the entire value, it's going to stick all your data on different backend servers instead of running it all in the same server, because you ran 1 through 100 as your partition key. So that's true, actually. Last one, any changes made to any item in any replica table are replicated to all other replica tables within the same global table. Hold on, let me just make sure I'm clear on this. Any changes made to any item in any replica table, oh, it's not replicated to all of the other replica tables in the same table. Is that true? That's let's think about that. Why even have a replica table if it's not going to replicate to all the other tables in the same global table? That doesn't sound right. That sounds false. Okay, so here we are, and you're going to basically create a DynamoDB table, create a global secondary index, add and update items in that table, query the global secondary index, and you're basically going to have an application that retrieves the CSV file from an S3 bucket and then loads the data into a DynamoDB table, and they're going to create and use any necessary secondary indexes, right? So same thing. Now with this lab, this is the same pattern that we followed yesterday. You're going to connect to your development environment, choose the one that you're going to use, and then you're going to roll down into the whichever one is, most important to you. Now remember, you are going to still have the solution available to you, and by default, the solution is being called. So again, make sure you refer to it if you feel like things are going south to see what you may or may not have missed. But, if you are not comfortable with code, then you're probably just going to review it. If you are comfortable with code, then man, give it a shot, code it out. Okay. This is what we're going to be doing for the remainder of the time here until we go to lunch, right? So let's give it a shot, and then we'll take lunch at 12:05. For those of you who finish early, we are going to be coming back at 1:05 p.m. to finish the rest of the day. Okay. Any questions?
What is the link for the lab again? Could you place that in the chat again, please?
Yes.
I didn't quite get
Wait,
what.
so Gerald, I'm sorry. Have you not started your lab then, since you're just now getting the link?
No, I haven't started it yet. I mean, yesterday, yes.
Okay.
Today,
All right. Sorry. Go ahead. What was your question?
I didn't quite get what a hotspot was. I think I missed that somewhere along the line. You
Oh,
mentioned.
yeah. So a hotspot is basically when you know, Amazon's going to spread your data across a couple of different partitions. Let me see if I can back up to this really quick. I think it was actually in the best. So just know that Amazon's going to partition your data in your partition key across a number of backend servers. If all your data is just like numerical, like you know, it's ordinal, basically it's like it's going in order, like the one that you see on the lower left hand side, you're going to end up with all your data on one backend server. You're not going to get the maximum number of reads and writes that way off of your DynamoDB table if Amazon puts all your data on one server. Now look at the one on the right hand side. Because they added a random suffix to the names, even though it's still starting with 200 to 289, you're now across like 2 or more servers because you've added a random pattern to the end, right?
Okay, I see.
So that's why you're avoiding hotspotting. Hotspotting is where you're overwhelming one of Amazon's backend DynamoDB servers because you left your data in an ordered fashion instead of adding a random hash or a suffix on the end.
And the solution to that is not to, as you said, numerically name your partitions, basically in order, in sequence.
Exactly. And the problem is that you won't know how your data is partitioned, but you can assume that if you have it in that sequence, it's going to get isolated to one box on the back end.
Okay.
Yeah, so that's just the best practice. That's all it is. Okay, just to check. Hopefully everybody is in queued. And no one is waiting. Okay, good.